Hi everyone. Thank you all for coming today. It's my pleasure to introduce our speaker, Mr. Changrui, and he just finished his bachelor from National University of Singapore, where he currently holds a position of a full-time research assistant. Yeah, what I found surprising about him is that he hasn't started his postgraduate journey yet. However, he has already published two papers at TCC and Europe, which are like a top tier conference in my research area of cryptography. So I really hope that you found his story encouraging if you guys are thinking about starting research at the early stage of your academic journey. So today he's going to share his recent publication at TCC this year on instance hiding interactive proofs. And for the conference of TCC, every year they will invite some papers into the journal of cryptology. They typically invite the top papers from that conference. And this work is one of the top papers in the TCC this year. So all right, Henry, the stage is yours.
Thanks for the introduction, and thanks for everyone attending my today this morning. Yeah, and my name is Changrui Mu, and today I'm introducing our study about the instant hiding interactive proof. This is joint work with my undergraduate supervisor, Professor at the University of England. Yeah, I just want to make sure, like right now, whether those people online can hear me clearly. Yes, someone, okay, sure. Nice.
Yes.
And okay, I beg your apology, like because today I can only go this slide by click my laptop, so cannot go that side. So I'll just thank you. Okay, so today we're introducing instant hiding proof. So interactive proof is a fundamental notion in cryptography and complexity theory, or in general theoretical computer science. In interactive proof, there's one party known as a prover interact with the other party known as the verifier, and the prover try to convince the verifier that some proposition is true. And in interactive proof system, in some case, both parties may hold some secret that they do not want the counterparty to know through the interaction. One of the most beautiful and infrequent example is the knowledge proof. And in the knowledge proof, the prover, the stronger prover, may hold some secret to prove to the verifier, yet do not want the verifier to learn its knowledge through the interaction. I want to check how many people have ever heard this term before this topic. Okay, cool. At least London. And yes, so the invention of the knowledge proof is revolutionary. Because the knowledge is such a philosophical notion that do not know how to define mathematics. And the knowledge proof simply define the fact that not learning knowledge without defining the knowledge itself. To get some intuition, so imagine you have a fortune to talk to the creator of the world, if any. And they want to learn the knowledge about, some truth about the world from it. But unfortunately, all it tells you is that there's good pasta in Italy. And you realize that you simply learn nothing from it. Why? Because you can't just figure this out yourself. You can try pasta in Italy and figure out what he said. So even if what he said all in plain text, meaning there's no input at all, but it seems to learn nothing from it. And this somehow captures the intuition of the knowledge proof. A little bit dive into the definition. So in the example I drew before, you don't learn anything from the creator of the world, because what he tells you is somehow not beyond what you can imagine or you can simulate by yourself. And this happens a lot in some old-fashioned conversation, like you, after talking for a while, seem to learn nothing, and this essentially capture the notion of the spirit of the knowledge proof. Formally, we say an entirety proof is the knowledge if the weaker party, the verifier or any verifier, there exists an efficient simulator that takes the input and output of protocol, basically what the verifier can see is supposed to see in the protocol. And the simulator can generate a distribution that is close to what we can see in the real protocol. So somehow this is to say that what the verifier see in the protocol is not beyond what it can generate by itself. Thus it learns nothing beyond the fact that the proposition is true in the proof. And formally, we will say this protocol is a statistical knowledge. If what the distribution that the simulator generates is statistically close to the verifier's view in the real protocol. And in the rest of the talk, we'll denote by SAK, the set of languages that have such a statistical knowledge proof. If you are familiar with this class, you simply remember this class that has such candle proof.
Sorry. Do you have a slide on what are interactive proofs?
Sure.
Yeah, I think they are not familiar with notion of interactive proofs as there's no computational complexity course at CUHK yet, right? I just installed that course, but it will begin maybe from the next semester. So they don't have any background about it.
Yeah, sure, cool. So
maybe
by far, like I won't give the full definition in a while. By far, like when I say entirety proof, you just think about like it's just there are two parties. There's one prover who is very strong, and there's a very weak party who is very weak, and they somehow like talk to each other. And the goal is that the prover want to convince the weaker party to verify that some statement is true. And
do you guys know what are like NP and P, a complexity class? Good. Yeah. When he's talking about a language, he means a language in NP. That's the point I want to make. The prover is trying to prove an instance X in some NP language. The knowledge he's talking about is about NP witness. For example, for graph three coloring, the X is just a graph, and the witness is a three coloring scheme. How can you color this graph? Just to clarify this. Sorry for interrupting.
Thanks for the explanation. Yeah, and I mean, if you find any part confusing, please feel free to impart me and ask me.
Yeah, because we have a relatively small group, so I want to make it interactive.
Yeah, this presentation itself is like an entirety. Trying to convince you something through interaction. So just
make sure it's not your knowledge.
Make sure it's not your knowledge, exactly. And yes, so by far like just so hopefully like you can get some intuition like what we mean by no knowledge, and this is from definition. So from a high level idea, the knowledge is to protect the prover's secret. Prover is a stronger one from the verifier. So somehow like the prover don't want the verifier to know its knowledge, so it's to protect the prover. And there are some situations the verifier may also hold some secret. In particular, for the verifier, the most important secret should be just the input instance. What Dr. Liang just introduced is like, for example, if you consider NP language, you want to solve an NP language, you have one instance. And NP language simply say that you can somehow get some short proof, deterministic proof. And given that proof, you can know that you can definitely show that it's inside this language. It's exactly inside the classes of strings that they want to accept. Yeah, and so this is an instance, like it's like the statement we want to prove. And so this is somehow the most natural secret for the verifier. And the spirit of this definition of instant hiding is somehow similar to zone knowledge. But in this case, when the two parties they want to make some proof to some statement, here this instance is private given to verifier. The prover doesn't quite know what instance it is proving. And we want to ensure that what the prover sees in the real protocol is not beyond what we can generate by itself without knowing the instance at all. Yeah, it's like the mirror of a zone knowledge group. So formally, right now let me define what do I mean by infinite proof and what do I mean by instant and infinite proof. So specifically in case of instant and infinite proof, in the beginning, the verifier is given an instance as input, and while the prover is only given the length of the instance. And then the prover and verifier, they make an interaction. In the end, the verifier decides either accept or reject. If it accepts somehow, it means like it believes that this instance is inside a language, which is a good set. If it rejects, somehow it's like it believes that this instance is not inside the good set, the language. Okay? And so we will require some components and sumness property for the infinite proof. This means that if, by fact, this instance is inside the language, then the honest prover should be able to make the verifier accept with high probability. On the other hand, if the instance is not in the language, then no prover is supposed to make the verifier accept with high probability. So if you think about NP, okay, maybe people are more familiar with NP. If consider any NP language, if the instance is inside the language, then there exists an NP witness that can make the verifier algorithm accept with probability 1. But if the instance is not inside the language, then there simply doesn't exist any witness that make the verifier accept in the end. So this is like a relaxation of the NP verifier. And additionally, in case of instant hiding proof, we will ask this instant hiding property. We already have some like intuition. Formally, we see the infinite proof is instant hiding if for any proof there exists a simulator that takes only the length of the instance and generate the prover's view in the real protocol. Because the simulator doesn't take the instance at all. So the distribution it generates somehow should be independent from the input instance of the verifier. So this essentially ensures the verifier's privacy even against the potentially unbounded prover. So this definition seems quite counterintuitive, because since this suggests that you can make some proof on a statement without even knowing what exact statement you are proving. I'm going to give a very simple example to you. Okay, I'm going to check like how many people are familiar with a group, like cyclic group. Okay, cool, nice. So let's consider a cyclic group with generator G, and we define a language to be the set of group elements whose discrete logs most significant B equals to 1. Okay? And now I'll show you that there exists a very simple instant hiding proof for this language. So in this case, the verifier in the beginning is given a group element as input. And you assemble some random R from possible orders and set the x prime equals to x times g to the R. Essentially, the x prime here is uniformly random loop element and independent from the input x. Okay? And they will send this x prime to the prover, ask the prover to compute the discrete log of x prime for it. So let's denote by z prime the discrete log of x prime. Suppose the prover behave honestly, then z prime minus r is supposed to be the discrete log of the input x. So the verifier can simply check that and verify whether the most significant b equals to 1. We notice that this total code is perfectly complete and stuff. By meaning this is that because here this z prime minus r serves as the NP witness for the language. So suppose the language is inside this, suppose the instance is inside the language, then there must exist this, then this z prime minus r will be this witness. But suppose not, then there's no witness, so you will be perfectly complete and so on. And it's also perfect instant hiding because what the prover see in the protocol is simply this x prime, which is the independent uniform random loop element. In particular, it's independent from the input. So it simply does nothing about input. Not only it's independent from x, but if you consider honest prover here, suppose the prover is honest, we are just compute the discrete log of x prime, and what we see is simply this x prime and z prime. These are efficiently sampled, this distribution. And these are some special cases of instant hiding proof. So a little bit formally, we say an infinite proof is epsilon instant hiding if the distribution that the simulate generate is epsilon close to the prover's view in the protocol. And for the special case we saw before, suppose the honest prover's view is efficiently simulatable. Then we call it the simulatable HIP. And in the rest, we'll denote by HIP the classes of language that have instant hiding proof, or HIP.
So in your previous example, I understand that the simulator doesn't need to know the exact X, but it does need to know some meta information, for example, the description of the cyclic group.
Cyclic group?
Yeah,
so that is considered a part of definition of language.
I see.
Yeah, good question. So you somehow can define classes of language.
Okay. Can I close that?
Okay.
Oh.
Cannot?
Just click OK. It will work. Maybe you should first get out of the whole screen. Get out of this mode. Yeah.
All right, thank you. So this is for definition of the instant hiding proof. And so in conclusion, this is hopefully the takeaway for today. The knowledge is a property that protects the prover's privacy, while instant hiding is a property that protects the verifier's privacy. And in the last few decades, there were many great work on understanding the complexity and the application of the knowledge. The knowledge has become the foundation of cryptography and will definitely continue contributing to the development of cryptography. On the other hand, our understanding about the instant hiding was much less. Despite they somehow capture the natural privacy property of the two sides of the protocol. So in this study, we want to understand the power of instant hiding type. Is it instant hiding type even possible? Or can every NP language have instant hiding type? And one also want to understand, because we want to do cryptography, we want to understand what's the relationship between instant hiding time proof and other cryptography primitives. We found that the two classes, the HIP and the SAK, they share many similarities. So we spend some effort to understand the relationship between them. And lastly, we also show some other property about the HIP class that we didn't know before. Okay, so for the first question, the how are instant hiding time proof? In previous work done by the freedom law in Gideon, they show that any perfect hiding HIP language is inside MP set 40, intersect 20 set 40. Is everyone familiar with these two classes?
No, I don't think you need to explain. Just yeah, something similar to NP, treated as NP.
Treated as NP and called NP. Okay. And in this study, we extended the result to any epsilon HIP, where the instant hiding error epsilon can be even as large as some constant. And for the special case, the simulatable HIP, we can even remove the nonconformity and show that the simulatable HIP is a subset of M intersect M. There was similar result found for SAK. And in particular, no NP-complete problem will have neither SAK nor HIP unless collapse of the polynomial hierarchy. And for the second, and then we also show some implication of hard HIP towards one-way function. So one function is a very fundamental notion in cryptography. It's a function that is easy to compute but hard to include. It's very important for cryptography. There's no one function, somehow cryptography doesn't exist for strong sense. And so we show that if there exists a language that is hard on average and has an instant hiding time proof, then there must exist one function. And for the simulatable HIP, we show a stronger result. In particular, we show worst case implication. We show that if any language that is hard on worst case and has this simulatable HIP, then there exists a one function. So this is what we show for HIP. There was similar result of a hard SAK implication towards one function. So given the similarity between these two classes, HIP and SAK, it's natural to ask what's the relationship between them. We answer this question partially by giving oracle separation of HIP from SAK. In particular, shows that there exists an oracle language that has an instant hiding time proof, but probably has no statistical proof.
Do you know the other direction?
Yeah, that is still open. That's a very interesting question.
Even with the oracle.
Yeah, even with oracle. So, but in fact, like when we don't quite know how to construct instant hiding time proof for some very natural statistical SAK language. For example, like graph isomorphism or like statistical difference problem. We don't know how to make HIP. So these are like evidence. Yeah, and lastly, we show that this HIP is has some very strong closure property. So it's like this. So consider any language, HIP language, defined by characteristic function f, and consider any polynomial size PG. Then we define a new characteristic function f prime to be G composed f, and then the new language L prime defined by this new characteristic function f prime also has the instant hiding time. And notably similar closure property for SAK is only known on the polynomial formula. So polynomial formula is a subset of polynomial circuit. So this gives us another evidence that these two classes seem different. So this is what we show in the study. And for today, due to the constraint of time and space, I will give a proof for one implication and the one on the upper part. So in the rest of the talk, I'll firstly introduce the idea of output of the average case part HIP into one function, and then I'll introduce the proof for HIP upper bound. In the end, I'll offer a set of open problems for the future. So firstly, we prove that the average case part HIP implication for the one function. We show that if any language that is hard on average and has instant hiding proof, then there exists infinite open non-uniform one function. So, in fact, this is what we show. So,
Can I ask
sure.
Maybe stupid question? Back to the previous slide.
Sure.
I just wondering what's this infinitely often then uniform means, because normally in cryptography we only call it one-way function. I don't know what this adjective means.
Yeah. Okay. So that's really good question, and that puzzles a lot of
We
people.
read down the definition on the board.
Yeah.
It just means for infinitely many security parameters you cannot invert. But you could be able to invert the function for an all-full parameter. Yeah, that's
About invertible or not?
Okay. So let me simplify the description. So let's say when we say A is hard, okay, what we really mean is that so there are two kinds of definition. One is that there exists some big number such that for any number bigger than this 0, A is hard. This simply means that this is a very continuous step. Yeah. And the weaker one is this infinite open. This somehow says that there exists infinite. It's like there exists an infinite set. Such that for any set, this set, AN is 1. So to prove by image, the first definition is like if this is n0, for the range, any value larger than n0, A should be hard. But for the second definition is that, okay, we still mark the n0 here, but we only ensure that there are infinite points, like 1 and 2 and 3, and so on. On this point, A is hard. This is bigger.
Thanks.
Yeah.
How about the non-uniform?
Oh, that's another question. So
it's interesting that you know the definition of one function, but you don't know what are non-uniform.
Well, in cryptography, we only use one function as one function.
Yeah, so
I suggest that we do not spend time on non-uniform, just ignore non-uniform. It's not as important as the word infinite. I think infinite often is important for you to understand.
Can I just understand it like just a one-way function?
Yeah,
Not
infinitely open one function.
so for today, whenever you see this field, what is this ignore?
Okay.
Yeah, we can go offline.
Okay.
Okay. So
No, I didn't promise to pay for her lunch. I'm kidding. You're welcome to join.
yeah, okay. So in previous work done by Imperial and Luby, they showed that there's one definition for distribution one-way function that is equivalent to one function. And in this work, what we did show is that this average case part HIP will imply distribution in one-way function. So in the rest, we'll focus on this implication. So first thing first, what do we mean by saying average case part? So we say the language is average case part if there exists an efficient sampleable distribution x, such that for any efficient algorithm, there exists a negligible function. If you sample instance from this efficient sample distribution, the probability that this algorithm can solve the problem is bounded by half-pass negligible. Okay, and in rest, we'll just assume this efficient sample distribution to be a uniform distribution for simplicity. Okay, and in rest, we're supposed to give the definition of distribution one way, but since these definitions are too complicated for this such talk, so instead, it will be much easier and sufficient for me to give to tell what does it mean if one efficient function is not distribution one way. So consider any efficient function f. If the function f is not distribution one way, then there exists an efficient simulator. And if you give the simulator a random image, you will be able to sample the pre-image of the function uniformly random. Yeah, in fact, there will be some error, of the sampling, but in this talk, we just ignore. We assume that this inverter is perfect. Whenever you give it a random image, it will give you, you will sample the image randomly. But we still need to make sure that the distribution that will feed to this algorithm is the image distribution of the function. Is the definition clear?
No. Even I didn't get it.
Okay. So consider any efficient function f.
Yeah.
If this function f is not distribution one way, then suppose you give this a, then there exists an inverter a.
Yeah.
Suppose you give the inverter a random image of the function. Here's a y.
Yeah.
Then what the inverter will do is that it will sample the pre-image of y uniformly for you.
You assume this f is efficiently invertible, at least.
No.
No?
We just start from any efficient function. It's efficiently computable.
Sure.
And then suppose it's not distribution one way. Then there exists this.
I don't see why you need to require that it's not distribution one way.
It's like I'm just trying to define the definition in the
Okay.
opposite.
So how much do I need to know about distributional one way to take the negation of it?
I suggest you know. It will be much easier to know the negation of the definition.
Yeah, can you explain a little bit on that? What does it mean by a function not to be distributional?
Yeah, sure. If a function, so if an efficient function is not distribution one way,
Yeah, what does that mean?
this means you will have an efficient inverter. What the efficient inverter will do is that if you give the efficient inverter an image of the function,
Yeah.
you will give you some pre-image.
Yeah.
And specifically, you will give the image you will give to you is a random image, pre-image. This random pre-image will sample over those possible pre-images mapped to this value y.
So in one-way function, the inverter trying to guess the exact value of the pre-image, but here you are just guessing the distribution of the pre-image. Is that?
Yes and no. So in one function, the inverter can only guarantee to give you one of the pre-image. But here the inverter is stronger. The inverter will give you a random pre-image. So let's say 1, 2, 3 are all mapped to value A. If it's a one-way function, the inverter is only ensured to give you one of the value of a 1, 2, 3. Okay? But here, if it's not distribution one way, then the inverter is stronger. The inverter will ensure to give you a random sample from 1, 2, 3. Like sometimes I'll give you 1, sometimes I'll give you 2, sometimes I'll give you 3. But if it's a one-way function, if it's not a one-way function, then inverter will only ensure to give you one of the pre-image. Maybe it will always give you 1, never give you 2, never give you 3. Okay, so that's a deal. Maybe I can draw on the right.
I think I get just a bad wording. I mean, you call it not. However, you do have a requirement that the way it inverts, it should be able to sample from the pre-image sets with a certain distribution that is close to the real distribution. That would it should be ipsum close to the real distribution.
Yeah. Yes.
Yeah, it's just a fascinating, I guess.
Yeah, exactly. So, okay, so for this code, just assuming just a perfect example of the distribution.
You can call it something like ipsum easy, like ipsum easy one function, something like that.
Oh, yeah.
Is that not distributional one way? Okay, I think I got it.
Okay. Yeah, so, okay, so hope everyone's clear about the definition. And so now given this definition, our task is clear. So we have a language that is hard on average, and we have an instant ID attribute for this language. In particular, the Wi-Fi algorithm for the language is efficient. And our goal is to show that there exists distributional one function. And to do this, the most natural way is to use standard cryptography reduction. So what is standard cryptography reduction? This is somehow usually how cryptography works. So here we have some assumption, and we have some efficient algorithm, the Wi-Fi algorithm. And we will use this Wi-Fi algorithm to construct some another function, f, in some way. The function based on f is based on the Wi-Fi algorithm. And we're hoping that this function f is a distributional one function. Suppose it is distributional one function, then what that? And suppose it's not, then we will have an adversary that is against the distributional oneness of the function. And in standard cryptography reduction, we will usually hope to use this orange adversary to construct a new adversary, this blue adversary, or blue algorithm that can solve this language efficiently. And suppose we can do this, then we'll make a contradiction that this language is not. This is how cryptography usually works. Unfortunately, in our case, this argument since doesn't work. It doesn't work is because here the orange adversary that we can get is not strong enough for us to make this algorithm to solve the language efficiently. And what we really did is what I call the adversary amplification argument. So I use an adversary to help us finding a better adversary towards our goal. Let's see how it works. So we will construct a function as before. Suppose this function f1 is not the distribution one way. Then we get this orange adversary, which is not strong enough. But it's okay, because this adversary is still efficient. So what we do is that we will use this adversary as a black box to construct a new function, f2. And suppose this function f2 is distribution one way, then we're done. Suppose it's not. Then we'll get a new adversary against the distribution oneness of f2. Moreover, we can prove that this new adversary, this green adversary, is stronger than orange adversary. In particular, it will be closer towards solving the problem L. And if the green adversary is still not strong enough, we can continue by constructing a third function f2. As long as we can prove that after the bounding number round of this argument, we can get a strong enough adversary for us to construct the efficient algorithm to solve the problem. Then we're done. In particular, in our case, it takes us just some polynomial rounds of argument to complete. Okay. But here's a remark. Yeah, so this proof technique can be seen as an extension of a previous work on this some multiple equation is a hash. So they use the adversary in a non-backwards way to make some construction. But there's a drawback. So firstly, by using this argument, in the end, our candidate function is non-constructive. Because we use the description of the adversary as part of the description of the function. And we do not really know what's the description of the adversary. So somehow we just prove the existence of some primitive without giving any concrete construction. And secondly, if we allow this adversary could be non-uniform or only defined over infinite over input set, then in the end we can only get a non-uniform and infinite over construction. Yeah, cool. So after seeing this overview of the proof, let's try to prove. As a warm-up, let's try to prove a weaker version of the theorem. Let's try to show that if there exists a language that is hard on average and that has one round perfect hiding instant hiding term proof, then there exists distribution volume function. So the difference is here is a one round and there's a perfect hiding. For this weaker theorem, the standard cryptography reduction is sufficient. Okay, so we have a one round instant hiding term proof. In the beginning of the protocol, the verifier is given the input instance and some random seed. It will be convenient to understand the verifier's algorithm as the next message function. So in the beginning, the verifier will take the input instance and the random seed and generate the message. This message we call U1. Send this message to prover, and prover responds with its message Y1. And this will be the transcript of the protocol because it's just one row. In the end, the verifier will look at the instance, the random seed, and the transcript. Decide either accept or reject. This is how the one round can improve works. And notably, because of the perfect hiding property, suppose any transcript that is valid transcript for one instance, then it must be valid transcript for all instances. This is because if one transcript is invalid for one particular instance, then this will leak the information of that instance. I mean, if you see that transcript, you can at least know that it's not that instance. Okay. And in particular, if we consider any valid transcript S and any instance X, and here we denote by RV the random seed space of the verifier. There will exist some subset of the verifier's random seed that are consistent with the transcript and the instance. We denote by beta XF this set of random seed. So, in particular, if the verifier in the beginning take any random seed from a beta XF, and if its input instance is X, then the verifier will output some message as in the transcript. So yeah, and this beta XS set is super important for the rest of the talk. So I'll pause for 1 minute and make sure everybody understands the definition. And please remember that there is a set called beta XS, which is the set of verifier's random seeds that are consistent with this instance and the transcript.
I think your definition as including the prover's response. So this side also depends on the initial prover.
Yeah. That's a good question. But imagine like what the prover response will not actually affect the set.
Yeah. My concern is you use the set. Remember that your P will not be.
Yeah. That will be a problem in the future.
Yeah.
We will see. Yeah. That's a very good question.
There's a very simple question. In my opinion, U1, you just consider U1 as Y. Why isn't this a Y function?
Yeah, that's a good question. That's a good idea. I mean, exactly, this is a one function. I'll show you.
Okay.
Yeah.
Yeah.
This is like too slow. And okay, so people may ask why we call it beta XS because there is an alpha set. There is an alpha. So the alpha is those random seeds in beta which the verifier accepted in the end. So the verifier in the end will look at the instance, the transcript, and the random seed, decide either accept or reject. So you will accept some of them and then reject some of them. And the alpha is those it accept in the end. Okay. And in particular, it can be proven that the probability that the total code accept in the end is equals to the expected ratio of the size of alpha excess over size of beta excess. This is anatomy of an entire group. Actually, this fact holds for any entire group. And in our case, because of this nice perfect hiding property, we can show that there exists a good transcript S, such that if the instance is inside the language, then the ratio of alpha access over size of beta access will be larger than 0.5. On the other hand, if the instance is not in the language, then the ratio of alpha access over ratio of beta access will be smaller than 0.1. And right now I want to convince you that if somebody can help you to sample an element uniformly random over the beta access field, then you can you can solve the problem efficiently. This is because the alpha access you can efficiently verify by running the verify algorithm to see whether this random C is consistent with the transcript and instance and whether it's accepted in the end. And
you verify is public one.
No.
Then if I don't know the verifier secret, how can I just verify from the transcript?
So the elements of alpha access are some random seed of the lab file. So given some random seed of the lab file, you can check whether it fell in the alpha access or not.
So then you don't need to give it S. S can be computed from
No, quite. Like S is composed of some verify message and
to
proof
verify it efficiently. I need to know both beta and S.
Yes.
Then if you just give me beta, I don't know S. How can I decide that?
It's like if you're given X and a random sample from a beta access, then you can decide that.
Yeah, but here you didn't give me S.
I will give you S.
Okay.
Yeah. So we do need the S as the non-uniform advice.
Okay.
It's like some string coded in the algorithm. Yeah, that's a question. I'll add this in the slide. Okay, so yeah, hopefully it's clear that if you can sample uniformly over beta access, then you can solve the problem. Now we'll define our candidate point function, distribution point function as following. So the function will take an input instance and the verify random seed as input. You will run the verify first message function to get this first message, and will output the instance together with the first message. Suppose this function f is not distribution volume, then we will have an efficient inverter as we introduced before. The inverter will take some random image. You will sample the pre-image uniformly. And because, as we can see here, the random image of a function f is simply the distribution of instance together with the first message distribution. And that is somehow equivalent to the instance and the transcript distribution. So the pre-image distribution of f is exactly beta access. And given this, we use standard cryptography reduction to compare. So suppose the function f is not distribution only. We get this inverter that we have. And we will define an efficient algorithm that can solve the problem efficiently as following. So the algorithm B will take this good advice, good transcript as a non-uniform device. And when it takes any input x, you will feed the inverter A with the instance and the transcript as input, and get a random sample from beta access. Then all you need to do is to decide whether this random seed fell inside alpha access or not. Because of the good property of this good transcript, then this non-uniform algorithm can solve this language division.
Modular to sample row as x, you need to run p. You don't need to run p because you replace p by a simulator.
Yes, exactly.
Okay. That's why you require that your work only works for simulator.
No, not really. So, because we already take this as a non-uniform advice. If it's non-uniform advice, we only require to exist this string, not like we need to efficiently sample this string also.
Yeah, but you cannot compute the row as x.
A row. In the equation.
Yes. Yeah, I think your A is efficient. As long as A is efficient, yeah, it's fine.
Yeah, if A is efficient, it's fine. Okay. And this shows this weak conversion with 0. But unfortunately, this argument cannot be extended to show the full proof. It will not even work for show 2-round perfect hiding.
10 minutes.
10 minutes, okay. So I'll finish this part of it. Yeah, so so I'll give like some idea why it doesn't work. Okay. So consider any 2-round perfect hiding protocol. In this case, these two parties are entitled for 2 rounds. So it will be like the following. So the buffer in the beginning will run the first message function to get this first message and send it to prover and get back the result. And for the second run, the second message function will take the instance, the random seed, and the first run transcript to generate its next run message and send it to prover get result. So right now the transcript will be 2 rounds of message, which U1, Y1, U2, Y2. This is different from the previous 1-round protocol. And now let's see how our previous candidate function will work here. Recall that we used the first message function to define our candidate one-way function, distribution one-way function. And in this case, the output distribution of the function will just be the distribution of the first run transcript. And then suppose this function f1 is not distribution one way, then we still have some efficient inverter. The inverter will sample some distribution for us, but we will only sample some random seeds that are consistent with only the first round of the protocol. And indeed, if some random seeds that are consistent with first round of protocol, they may not be consistent with the full transcript. And we do need to sample uniformly over the beta access, which are those randomly consistent with the full transcript. So this candidate doesn't work. And our second attempt is to use the second message function of the web file as following. So we have pasted the instance, the random seed, and the first round of transcript, and output basically the transcript of the code. But the problem right now is, as what Dr. just suggested, the Y1, which is the prover's message, may not be efficiently sampleable. And thus this function f1 prime we define itself may not be even efficient. So this also fails. And what we really did is this adversary amplification argument. We will define the f1 as before, and if it's not distribution one way, then we'll get the inverter that sample random seed consistent only with the first round. And then we will use this inverter to define our second function. You will be as following due to the time constraint. Maybe I'm not able to expand it. But roughly speaking, we can prove that by defining in this way, the F2, the output distribution will be just the image distribution. And thus, suppose it's not distribution one way, we will get the inverter that sample uniformly over those random states consistent with the full transfer. And once we can get this efficient inverter that samples uniformly over beta access, then we can decide, we can solve the problem. Yeah, and to extend this argument to the general instant and infinite proof for any polynomial, we will simply run this argument recursively. So in the beginning, we get we define some function with only a first round message function, and we get some inverter that sample uniformly over beta, just the first round, consistent with the first round message. And then, suppose it's not distribution, we can sample consistent with the first two rounds and the first three rounds up to the last round. Suppose we didn't find any distribution one-way function yet, then we can get an inverter that sample uniformly over this beta access. And then we can, given this adversary, we can construct the algorithm the same way and solve the language efficiently. And thus, this will contradict our assumption that this language is a hard language. And but in the root, there are some remarks. So in the root case, the inverter, by the definition of the distribution one way, will not be perfect. That means there will be some error. Like the distribution of sample is absolutely close to the uniform pre-image distribution. So it will take a very complicated algorithm to solve this problem. And also in the real case, because due to some hiding error, we cannot really prove that there exists this good transcript at the result. What we really did that we will show that the instant hiding property is close on the parallel repetition. And thus we can do a strong amplification of the completeness and soundness error to make the error super small. And we can get some good transcript in there. So yeah, this shows theorem. So the theorem said that if any language that is actually hard and has instant hiding proof, then there exists infinite open non-conformal functions. Yeah, so due to time limited, so probably I'll skip the second proof. I'll jump to the conclusion. Yeah, so these are our main results. So there are some science results. We will mix the connection with some other interesting class too. But for this talk, this So for the future, we really want to understand for this class HIP whether there exists any natural complete problem for this class of language. Notably, there is a very beautiful construction of a complete problem for the SAT class, which turns out to be very powerful tool in the research of cryptography and complexity theory. And it will be cool if we can find the complete problem for HIP, given that they are natural counterpart of each other. And the second question is, can we find other, is there any other cryptographic consequence of existence of a hard HIP problem? So in this work, we show that the hard HIP will imply one function. The question is whether this will imply some more structured cryptographic primitive. And last question is, I think it's quite intriguing to properly define the computational version of an instant hiding proof and understand what the hardness that we need to make this kind of proof, to make it useful. Yeah, okay, so I guess that's all for today. Thanks for this. I'm happy to take any questions.
Do you have any questions?
Actually, I'm a little about cryptography or computational theory, but So forgive me if I ask silly question. So I learned the concept of zero knowledge proof in blockchain. So I think one question I want to ask is zero knowledge proof able to solve the problem of trust? Because in decentralized apps world, people are very interested to know. Okay, if I'm a client, I want to ensure that the server has executed some, for example, code for me to solve my problem. So, for very ordinary applications, for example, if I claim that I host a service computing the square root of a number for the user, so is it possible for you? Is it possible for me to give user some kind of proof that I indeed give you the square root of a number instead of some wrong result? And if so, would the cost of providing such certificate exceed the cost of computing itself? Yeah.
So, okay. So, your question, actually, it has nothing to do with this talk, right?
Yeah.
You are basically asking me about cryptography questions.
Yeah.
Sure. Do you want to address this question, or you want to spare it to me?
Yeah. So I'm not like a super expert in blockchain. Yeah. I thought like in blockchain maybe there are some application of system to make some layer 2 blockchain and somehow like the proof rate like goes on trusted machine and the EVM they verify it. And yeah, I guess like you can think about like where like what this privacy property of is a knowledge or is an ID can be applied in blockchain to add some function to this EVM. But I'm not an expert in that because I cannot.
His question related to your talk in the following sense. Basically, you're asking if I'm a client and there's some computation I don't want to do. I'm lecturing about this. Feel free to go if you don't want to listen to this. He's asking like, this is a very typical application. There is a server. To make you interested, this is ChatGPT. Okay? The moment you want ChatGPT probably you say. So ChatGPT is a huge model, and you as a weak server yourself, you are not able to run the whole model on your own device. So you may delegate some condition out. For example, you send some query Q to the ChatGPT, and ChatGPT answer with some A. For example, this is a picture. You ask ChatGPT that this picture contains a cat. Object detection, right? The answer is yes or no, right? So this kind of computation, ChatGPT, the latest version should be for all, right? However, this version is cheap. This version is expensive. They also have cheap versions, something like ChatGPT Mini or any. Maybe even they are running a very simple, probably RNN, very simple neural network, much simpler than ChatGPT. How do you believe that? When ChatGPT or when the server answers your question, they are really using this latest version. For example, if you are subscribed to it, how do you convince? How could they convince you that they really did this computation using this model instead of cheating using a similar model, right? That's the question he's asking. He called this problem the issue of trust. I'm not sure if this should be called trust, but just using his word, let me answer this question. The question is, yes, we have some cryptography tools to solve this problem. There's something called, he just talked about, it's called interactive proof. This primitive has two properties. One is basically, we call it completeness. This is also what they just mentioned, completeness. Another property is called soundness. So completeness, I won't give you a formal mathematical definition, I'll just give you intuition. Completeness says if something is true, you should be able to prove it's true. Soundness just means that if something is false, you should not be able to cheat. For example, we have some interactive proof. This is a cryptography primitive, or you also learn it from a computational complexity maybe. So there is a tool such that he can generate a proof together with this answer. With his answer menu, he also gives you a proof pi. And you as a client, you can verify this path to get a bit. This bit is an indicator, indicating if this guy is using this model as he should or not. And this proof is this proof has these two properties. Confidence means yeah, if he's using this, you should be able to learn b equals 1, meaning that you are convinced. However, if he's cheating, if he's using this model, then this bit should always be 0. You will always catch the server. And the first question is like, yes, you can have something like the interactive proof to solve for this problem. And then he asked the second question. If I choose to verify this proof, how expensive or how much resource I need to verify it? If my verification of the proof is as expensive as running this model by myself, there's no point, right? I can just host the whole model at my own location. I don't delegate my computation out. So to make this notion useful, we have another notion called succinct interactive proof. This word succinct just means that the time you spend to verify this proof should be much shorter than running the whole computation by yourself. If you are interested in this, search online this notion of succinct interactive proof, or someone doesn't like the nature of interactive. I mean, interactive means you may need to talk to this server a lot of times to be eventually convinced. The best you can hope for is he just send you a proof just like this. Just one single run communication. And then you can just go back to your home, verify the proof yourself, right? If you have that notion of that version, one round interactive proof, we call it non-interactive proof. So this is the final answer to your question. Succinct, non-interactive proof. This is when this guy answers you, he gives you a certificate or proof you can verify. It's non-interactive, meaning that this proof just comes in one round, and it's succinct, meaning that the time it's going to verify is much shorter than the model. And you know, there is a version. Proof is something very, very strong. A weaker notion of proof is called arguments. I wouldn't explain what are arguments. But anyway, they are basically try to understand arguments as proof. Then this constitutes one of the most hot topic in today's cryptography and security research. This notion nowadays is known as the SNARP. So succinct, non-interactive, ARG, SNARP. Yeah. If you want to know this application or to your question, the answer to your question, search online for SNARP. This is very popular.
Thank you very much.
Yeah. Yeah, and then I think, again, thank you, Changrui, for this very insightful talk, and I hope you guys found this talk as interesting and inspiring as I did. So, then we are going for lunch. You're welcome to join. Yeah, you. Yeah, indeed, if you are interested, you can join. And if you, maybe I should introduce myself first. You know, I'm a new faculty here. I just joined 2 months ago. I work on cryptography and quantum computing. If you are interested in thinking in this area, you should come to my office and talk with me. Yeah.
Thanks.
Yeah. Then a big applause for Rick.